on NASA to release the image.
That in fact NASA plans to release those images in a few days, in the middle of next week.
In the past few months, astronomers have witnessed something in our solar system that has left even the experts shaking their heads. An object flying in from interstellar space named 3I, Atlas, has just passed its closest approach to the Sun, the perihelion, and what it's doing now is nothing short of unbelievable. Jets millions of kilometers long, mass loss that breaks the laws of physics, a retrograde orbit, and behavior we've never seen from any natural object in recorded history. Welcome to Beyond Gravity Gates, where we venture past the limits of our solar system and unravel the mysteries that defy the laws of physics. Today, we're going to break down what is actually happening to 3I, Atlas after perihelion, what scientists think is going on, and why this object could rewrite what we know about interstellar visitors. 3I, Atlas, is an extraordinary object because it is one of only 3 interstellar visitors ever confirmed to pass through our solar system. The 3I in its name indicates that it is the 3rd interstellar object, following in the footsteps of 1I, Oumuamua, discovered in 2017, and 2I, Borisov, discovered in 2019. Interstellar objects are fundamentally different from the comets and asteroids that populate our solar system. They are not gravitationally bound to the Sun and have originated in completely different star systems. This means that 3I, Atlas, has been traveling through the vast emptiness of interstellar space, potentially for millions or even billions of years, before finally entering the gravitational influence of our Sunday. Because interstellar objects carry the physical and chemical signatures of the environments in which they formed, studying them provides a rare opportunity to glimpse the processes and materials that exist around other stars, making 3I, Atlas, a highly valuable and scientifically significant discovery. From the very beginning, 3I, Atlas, displayed several characteristics that set it apart from ordinary comets or asteroids. One of the most striking features is its orbital inclination. Unlike most objects in our solar system, which orbit the Sun in a relatively flat plane known as the ecliptic, 3I, Atlas's path is extremely tilted relative to this plane. Its steeply inclined trajectory immediately indicated that it was not formed here, but rather was an interstellar interloper arriving at a high angle that is atypical for objects native to the solar system. Additionally, its approach speed was unusually high. Objects that originate within our solar system are bound by the Sun's gravity and generally follow predictable velocities. Interstellar objects like 3I, Atlas, however, carry the momentum from their home systems, allowing them to travel at much greater speeds. This high velocity was a key clue to astronomers that the object was truly from another star system and had not been ejected from the solar system itself. Another unusual aspect of 3I, Atlas, is its spectral signature, which is essentially the unique chemical fingerprint astronomers detect by analyzing the light reflected off the object. While some components of its surface composition were consistent with materials found on familiar solar system comets, other expected elements were absent or weaker than anticipated. Furthermore, it exhibited chemical characteristics that do not commonly appear in local comets, suggesting that the conditions in its original star system were markedly different from those around our Sunday. This spectral uniqueness, combined with its trajectory and velocity, marked 3I, Atlas, from the outset as a particularly enigmatic object and one worthy of close study. As 3I, Atlas, approached the Sun and passed its perihelion, its behavior became even stranger. Unlike typical comets, which generally follow predictable patterns of brightening and outgassing as they near the Sun, 3I, Atlas, displayed anomalies that puzzled astronomers. Its increasing brightness, the nature of the material it was ejecting, and subtle changes in its trajectory all suggested that it was not following conventional cometary physics. These early observations hinted at an object that was not only interstellar in origin but also physically unusual, challenging scientists to reconsider some of their assumptions about how interstellar objects interact with the solar environment. In short, 3I, Atlas, began as an already intriguing visitor from another star system, but as it drew closer to the Sun, it became increasingly clear that it was a cosmic anomaly unlike anything previously observed. On November 9th, astronomers witnessed one of the most extraordinary and unexpected displays of activity ever seen from a comet or interstellar object. Using high-resolution telescopes, they captured jets of material streaming from 3I Atlas that extended up to 3 million kilometers into space. To fully appreciate the scale of this phenomenon, consider that the average distance from the Earth to the Moon is about 384,000 kilometers. These jets were more than 7 times that distance, a staggering size that dwarfs nearly every previously observed cometary feature. Even more striking, the extent of these jets was roughly 3,000 times larger than the faint glowing cloud detected by the Hubble Space Telescope just a few months earlier, suggesting an unprecedented surge in activity as the object passed perihelion, the closest point in its orbit to the Sunday. What made these jets truly extraordinary was not just their sheer size, but their direction and structure. Most comets develop a single, prominent tail that points away from the Sun, shaped by the solar wind, a continuous stream of charged particles flowing outward from our star. This tail forms because sunlight heats the comet, causing ice and volatile materials to sublimate, creating gas and dust that are then blown away by the solar wind. But 3I Atlas broke this pattern completely. Instead of a single, predictable tail, it displayed multiple jets, some of which were pointing directly toward the Sunday. These anti-solar jets were seemingly pushing against the solar wind, defying the standard physics that governs comet behavior. For a comet to generate jets that can oppose the relentless force of solar wind, the material being ejected must be extremely dense and powerful, and the energy required to sustain such phenomena is extraordinary. The implications of these jets are profound. Not only do they indicate that 3I Atlas is undergoing massive outgassing or possibly fragmentation, but they also suggest that the object is releasing enormous amounts of energy in a very short period of time. This behavior is unlike anything observed in typical comets, which gradually release gas and dust in predictable patterns. The fact that 3I Atlas is ejecting material both toward and away from the Sun, in addition to displaying jets millions of kilometers long, has left comet researchers both amazed and perplexed. Such activity indicates that this object is highly unstable and energetic, and it challenges scientists to rethink the physical processes that could be occurring on or within an interstellar body of this size. In short, the perihelion passage of 3I Atlas revealed violent, explosive behavior on a scale rarely, if ever, seen, and it set the stage for ongoing investigation into the true nature of this enigmatic interstellar visitor. One of the most puzzling aspects of 3I Atlas's behavior is the enormous amount of material it appears to be losing, especially when compared to its total estimated mass. Astrophysicist Avi Loeb and his colleagues calculated that, based on the observed acceleration and the jets detected during perihelion, 3I Atlas is shedding roughly 50 billion tons of material every month. To put that in perspective, this is an amount of matter greater than the combined mass of all major human-made structures on Earth by many orders of magnitude. What makes this truly baffling is that the entire object is estimated to weigh only 33 billion tons. In other words, the rate at which it appears to be losing mass exceeds its total mass, a contradiction that seems, at first glance, physically impossible. This apparent paradox immediately raised questions among astronomers. In normal cometary physics, objects of this size can release only a fraction of their total mass through sublimation and outgassing. Comets like Halley or Hale-Bopp lose material gradually over many months or years, and their total mass remains largely intact during any single perihelion passage. The numbers for 3I, Atlas, however, suggest that it would not have been able to survive even a single month without disintegrating entirely. This mismatch between observed mass loss and estimated mass indicates that either the object is breaking into smaller fragments, or there is some other unknown process at work. Fragmentation provides a plausible explanation for these extreme numbers. If 3I, Atlas, has shattered into multiple pieces, each fragment would expose new surface area to the intense solar radiation at perihelion.